let's continue with a couple more examples of separable differential equations. So for these examples, I've just copied my same instructions from our first video. Let's just find the solutions to the following differential equations. If there is no initial data given, then we'll just find the general solution. But of course, if initial data is given, as we see here on this example, then we will find the specific solution. We will find the actual solution given that initial data. So let's go ahead and jump into it. So again, when we're working with differential equations, what we want to do is find a solution, a function that will satisfy this equation when 3 secant of t times the derivative of y of t is equal to 1. So what we're looking for here is a function y as a function of t, if we can explicitly find it, a function y as a function of t that would satisfy this differential equation. So what we're going to do is we're going to look first and see if we can separate the variables into a function of t and a function of y. And we can fairly easily do that. The t's are right here. There is no y, there's just the constant. So we can definitely separate t's and y's. I almost said x's and y's, but we're t's in this case. And we can solve using our techniques of integration. So on this one, I'm going to start by dividing. I'm going to zoom in a little bit. I'm going to start by dividing both sides by 3 secant of t, 3 secant of t, and then I'm going to find dy dt is equal to, this actually becomes 1/3 cosine of t, and I'm going to separate the differential. So I'm going to move the dt to this side with the function of t so that I will be able to integrate both sides and determine the solution. So y is equal to 1/3 times a sine, almost, excuse me, times the sine of t plus, now there will be an integration constant on both sides, but we'll group them together as the integration constant on this side. Now this is actually our general solution, and it is an explicit formula because this is y of t. We've written it explicitly, y is a function of t. 1/3 sine of t plus c. Now we have this initial data right here, so we're going to go ahead and find that constant by plugging it in. So y, change my pen color, y of 0 is equal to 1/3 sine of 0 plus c. So c is, and that equals 1. So c is equal to 1, and my explicit function that would satisfy this differential equation is y of t, 1/3 sine of t, and the constant we just found was 1. So we're able to solve that initial value. It was a separable differential equation. We separated the variables and then we integrated both sides and used the initial data to find that constant. So that's our answer for that one. Let's take a look at another one. Okay, so let's take a look at this problem. So y prime of x is equal to y over 36x squared plus 1. So we can see right here that it is already separated. So this is definitely a separable equation. We're looking for the solution y of x, if we can write it explicitly, but we're looking for a solution to this differential equation. So a function that would satisfy this differential equation. I'm going to go ahead, because I want to be able to separate my differentials, I'm going to write y prime as dy dx equals y over 36x squared plus 1. I'm going to separate the differentials by dividing both sides by y. So I get I'm going to separate the functions and the differentials all at the same time. So I'm going to get 1 over y by dividing both sides by y equals 1 over 36x squared plus 1, and I'm going to multiply the dx to the other side. Now I'm going to integrate both sides in order to find the solution here. So when I integrate, I get the natural log of the absolute value of y is equal to, now when I integrate this guy, going to use some integration techniques, and I notice here that 36x squared is a perfect square. It's 6x quantity squared. So doing a little u sub here to see what this is going to be, because this is in the form of inverse tangent, but let's do the u sub to adjust for that constant. So du equals 6 dx. So dx is actually 1/6 du. So I'm going to just rewrite that over here. So this is 1 over u squared plus 1, and my dx is 1/6 du. So when I integrate that, 1 over u squared plus 1 is an inverse tangent. And we have the 1/6 constant. So now down here, natural log of the absolute value of y equals, we're going to get 1/6 inverse tangent of u plus an integration constant. But of course, our u was 6x. So went through a lot of steps on that just to remind us of our u subs and our inverse tangent formula, but you may have recognized that earlier on with that 1 over 36x squared plus 1 and been able to jump straight to that inverse tangent. Okay, so right now we actually have a general solution, but it is solved for implicitly. So right here, this is an implicit solution to our differential equation. So we've got an implicit solution. We'll highlight it because it is one of the solutions, but I could actually go through a little bit more work. This one we could come up with an explicit formula for, or explicit function. So let's just come up here and play around with that a little bit and see what we end up with. Now, let's keep in mind on this one that we did not have any initial data. The original problem was just given to us as a generic differential equation, no initial data. So we are just coming up with a general solution here, and we have the general implicit solution. But what if we wanted to solve for y, get this y as a function? So what if we wanted y as a function of x? We wanted to do this explicitly. Well, what are we going to do? Here we've got a natural log, so if I wanted to solve for y, I could exponentiate both sides so that the absolute value of y is equal to e to the 1/6 inverse tangent of 6x plus some constant c. Now we have solved for y, but if I want to get rid of the absolute value, I just have to remember that y would be plus or minus e to the 1/6 inverse tangent of 6x plus c. Now, I guess we could leave it in this form. This is explicitly, we have represented y as a function of x at this point. But there's a little bit more we could do with the exponential because I got that plus. And so we could write this as plus or minus e to the 1/6 inverse tangent of 6x and e to the c. But e to the c is just a constant, so I could write that as e to the c. I'm going to put it in the front. E to the c, remember, is just a constant. Plus or minus e to the c. This is just a constant. Let's keep that in mind. Write the rest of it. 1/6 inverse tangent of 6x. Now, this is just a constant. And remember that a constant can be positive or negative. So we could literally just take this whole thing right here. Let's circle it in red. We could take this whole thing and just define it as c. So let's just call that some constant c. C could be positive or negative. And we could write y of x equals c times e to the 1/6 inverse tangent of 6x. Now, given any sort of initial data, we would be able to find that actual value of c, positive or negative. We'll go ahead and highlight that. And that is my explicit solution. So down below we had the implicit, and up here we have found our explicit solution. And kind of simplified it down with that behavior of the constants in the exponential functions. All right, let's look at, get it all on the screen there. Let's look at another one. Let's look at our last example here. So the sixth example, hold on, let me move this over a little bit. All right, so once again, we're looking at a differential equation. U prime of t is equal to u over t to the 1/3. So I'm looking for, grab the wrong pen, I'm looking for u of t. Now we also, in this particular case, a solution to this differential equation. I'm looking for a function of t, u as a function of t that would satisfy this differential equation. Now we also have some initial data, so we'll be able to use that initial data to find any constants that we end up with. I'm going to go ahead and write this, so I'll be able to separate the differential as du over dt, the rate of change of u, over with respect to t. And at the same time, because I know I want to separate this, and I'm kind of thinking, can I separate this? And yes, I could definitely separate this differential equation into a function of u over a function of t. I can separate the u's and the t's into two functions. And so doing so, I'm going to go ahead and divide both sides by u to the 1/3. So I get 1 over u to the 1/3 du. I'm also going to separate the differential, 1 over t to the 1/3 dt. And I'm going to write that as u to the minus 1/3 du and t to the minus 1/3 dt. t. And now I've separated them, I've separated the differentials, I can integrate both sides of this equation and some similarities on both sides, just different variables. We get u to the 2/3, and we're dividing by 2/3, so multiplying by 3/2. Of course, there's an integration constant, but I'm going to write it on the right side. This is t to the 2/3 and 3/2 plus some integration constant where we've grouped the integration constants together. Now, what's kind of funny about this one is we have that common constant on both sides. So just to clean it up before I do anything else and plug in values, let's multiply the whole equation by 2/3. Doing so, this will make this u to the 2/3 equals t to the 2/3, plus technically we get a 2/3 times c. But we've talked about this a little bit, right? When we're working with those constants, multiplying that constant by a constant, it is still a constant. So I'm just going to write it as c. It is still a constant. Okay, now at this point, we could leave it here. And solve for our c, which is what I'd like to do. Solve for our c and then find the explicit formula, or we could find the explicit formula and then plug in our values. But I'm looking at this really quickly and I'm thinking this is going to be nice and easy to plug in. So let's pause right here and let's find the constant, and then we'll talk about implicit, because obviously this is an implicit relationship right now between u and t, but we could find the explicit as well. So let's go ahead and plug that in. So u, it's off the screen, so I'm just going to rewrite it here. U of 0 is equal to 64 was our initial data. So I'm going to go ahead. So when t is 0, 0 to the 2/3 plus c, u is 64, 64 to the 2/3. And so 64 to the 2/3, that is the cube root of 64 squared. Another way to write that is equal to c. So c is equal to the cube root of 64 is 4, and 4 squared is 16. So my c is 16. So u to the 2/3 equals t to the 2/3 plus 16. And that, I'm going to circle these both so we can write them like we did on the last one. That is my implicit solution. But we can easily solve for u in this particular case. So we could raise both sides to the 3/2. So u as a function of t would be t to the 2/3 plus 16 raised to the 3/2. And that is my explicit formula, or my explicit solution. And so just, if we can, we want to take it as far as we've done here into its explicit formula, u as a function of t, but we can also write it in its implicit formula. Sometimes we are unable to write it in its explicit solution, so we just write the relationship between the variables in an implicit form. But in this case, of course, we could not only write it in its explicit solution, but we were also able to find that constant because we had some initial data for the specific solution. All right, and that wraps up our examples on separable differential equations.